We're going to use this activity to test to see if a six-sided die is what we would consider a fair die, and also as an introduction to the chi-square distribution and one of the basic tests that we can use the chi-square distribution for. So one of the first questions we have to ask if we're going to roll a die and see if the die is fair is how many times will we need to roll it? You can see that we're going to end up rolling it 120 times. But how many times do we need to roll it? Like, for example, if I only rolled it 6 times, would I really be able to, if I rolled it 6 times, I'd expect to get one of each number. And we know from studying statistics so far this year that it's really unlikely that you'll get one of each if you only roll it 6 times. So the question becomes, how many times do we need to roll it? And we'll talk about that condition. It's kind of a similar condition to a normal distribution, but the big difference is the chi-square distribution looks like this. It's a skewed right distribution, and it's useful for situations like this. So one of the things that makes the chi-square distribution much easier in terms of conditions is that there is no condition for normality, but we do have a condition for a sample size. We do need it to be a certain size in order to make an informed decision, and this is a good example of it. So we'll revisit that in a moment, but for now we need to know we're just going to roll this die, and I have the die. I'll take the heavy lifting out of this for us, and I'll roll the die 120 times. But we'll revisit this. This is a good question. The correct answer to this is going to be 30. All right, not because the n equals 30 rule that we've had in the past, but for chi-squared, what we need is the expected counts. Okay, these numbers down here always have to be greater than or equal to 5. So it's a pretty easy rule. We need these to all be greater than or equal to 5. So really the minimum number of times we need to roll this would be 30. If I rolled the die 30 times, then I'd expect 5 of each of these. And what the idea of the chi-squared, what it does is it compares what you expect to happen to what actually happens. And if that difference is really big, sort of like residuals, if there's a big difference in that, then we would conclude that it's not likely that that would happen by chance. And we would conclude in this case that that the die is not fair, or that doesn't follow the distribution of a fair die. We're gonna do more than the minimum amount. We'll roll it 120 times, and like I said, I'll record the results in the table for us. Okay, so we can see the results in the table up above after rolling the die 120 times. We want to see, is the die fair? If the die is fair, what would you expect the distribution of outcomes to be? Again, we'd expect this to be uniform, right? Equally likely, right? This is a distribution that would look, something like this. Rather than a normal distribution, we'd expect all the bars. We don't expect it to be mound-shaped. It's symmetric, but all the bars should occur about equally likely. Okay, so that's what we call a uniform distribution. It is symmetric, but it's not mound-shaped and symmetric. So how many should I have expected of each? I should expect 20 of each. Okay. And you'll see on your formula sheet, the chi-square statistic is pretty easy to calculate. It's the observed minus the expected. We square that quantity and divide by expected. And of course, you see this summation activity or symbol over here that means to add all of those up. So let's hash out what that would look like. If we were to think about taking a summation of that quantity, observed minus expected, squared each time, divided by expected, what would that look like? So for the first one, we'd have 23 minus 20. We're going to square that, and we're going to divide that by 20. Then we're going to take in the next one, 20 minus 20, square that, and divide by 20. Then we have 19 minus 20, square it, and divide by 20. 17 minus 20, squared, divide by 20. Again, 17 minus 20, squared, divide by 20. And then finally, 24 minus 20, squared, and divide by 20. So we don't want this to be just our opinion if this number is big. We can see if the differences between the expected outcome and the observed are large, then we would conclude that the die is not a fair die. But let's think about what would lead us to believe that, and that's where we have to look at our chi-squared distribution, which you can see on your formula sheet. If I scroll down to that, it's a similar table to what we have with the t distribution and z distribution. But we have degrees of freedom and then probability that these statistics would occur. So the larger degrees freedom basically is going to mean that we took bigger samples. I'll explain how we've come up with our degrees freedom in a minute. But up here in the top is telling us the probability that these instances would occur. Well, if that probability is really low, right, less than 0.05 or 0.01, then we would conclude that the die is not fair. So our null hypothesis would be something like, the distribution of this die follows the distribution of a fair die, right? That it's not any different than any regular die. It has a uniform distribution. So the way you can articulate your chi-squared null hypothesis is a lot simpler and looser than what we've done in the past. It doesn't have to be as precise. You kind of just say it in words, articulate what it is in the context of the question that we're answering. So let's take a look at what we get for our chi-squared statistic here. Okay, so I get a value of 2.2, and what I'm going to do here is what's called a chi-squared goodness of fit test. So this means, is this claimed distribution 1, 6, 1, 6, 1, 6, is that a good fit for this die, or does this die fit that distribution? So our null hypothesis is that the die follows the distribution of a fair, and the alternative to that would be that the die does not follow the distribution of a fair die. So how do we make sense of this value of 2.2? Well, we need degrees of freedom is going to be n minus 1, where n is the number of categories. Or number of categories that the variable could take on. It doesn't have to be quantitative. This could be colors of Skittles or M&Ms if we wanted to test that distribution. So in this case, there are 6 values it could take on. So we want to think about 5 degrees of freedom and what that would look like on the chi-square distribution. So if I go to my chi-square distribution and I find my 5 degrees of freedom row and I roll out, I'm going to see that for a p-value of 0.25, I'm already at 6.6, okay? So what that means in terms of the chi-square distribution, if I come back to a graph here, if I go out to 6.6, the area to the right of that is 0.25. Well, the area to the right of 2.2 then would be much bigger than that. So it tells me my p-value for sure is greater than 0.25. Okay, but we can get a precise p-value. I'll show you how that works on our calculator in a minute. So I first just communicate a couple things to my calculator. I give it my observed list, which is in my L1, and my expected list, which I put in L2 here. And now when we go to stat and test, which should be the familiar menu for us, we're going to find an option on here that we have not used yet. We want to find this chi-square goodness of fit test. The other chi-squared test we'll look at later in this chapter, but our goodness of fit is really simple. We just need 2 lists. We tell the calculator our degrees of freedom, happens to be 5 here, and then we calculate. Okay, so you can see they got the same chi-squared value we got, 2.2, but they give us a more precise p-value, 0.82. So we know what that means, a p-value of 0.82 more precisely. Okay, 0.82. It means we would fail to reject H0, right? And this is going to sound like a double negative, but it's a correct way to articulate this. We do not have significant evidence that the die is not fair. That's the way our justice system works. That's the way our hypothesis testing works. So we do not have significant evidence that the die is not fair. And I think I mentioned to you all that I once was on a murder trial in Camden, which was very interesting and a really neat experience. But when we came back with our verdict of innocent, it wasn't because we had significant evidence that he was innocent. We never needed that. We were told from the start that we were to believe the defendant was innocent. unless there was significant evidence contrary. So if I were to articulate our conclusion that he was not guilty, it was because we did not have significant evidence that he was guilty. It wasn't, I wouldn't say we believe he's innocent because there's significant evidence that he's innocent. It's not what we were required to look for. We were looking for evidence in the other direction. So even though this sounds like a double negative, it's the right way to articulate that. So we would conclude we do not have significant evidence that the die is not fair. And that's your chi-squared goodness of fit test introduction.